Hello everybody, this is Mr. Walters and Human Anatomy and Physiology. We are talking about the action potentials. Action potentials are the common language of the central nervous system. The world out there is crazy. It's filled with lots and lots of different stimuli, sound stimuli, touch stimuli, chemicals, etc. So what's going to happen is we're going to receive that information with the sense organs, and then we're going to convert that information into an action potential, send it to the brain, and process it, and then elicit a motor response. All right, but what exactly is an action potential? What I want to do, let's look here. This is the axon. So we're going to focus in on an axon of a typical nerve cell. And what I want you to look at here, we've got the inside of the axon here, and we've got the outside of the axon here. Go ahead and make a copy of this right now. I'm having a sip of coffee. It's a little bit bitter. We have bitter taste buds. Coffee, the fuel of education. By the way, that's my fuel. Shouldn't be yours. You're too young to get addicted to coffee like me. Learn from my mistakes. Well, here we are. What's going on here? On the inside of the axon, we have a large number of anions. These are negatively charged molecules, polyatomic anions. For example, we can have phosphates here. PO4, 3-. These are impermeable. So in other words, they're stuck on the inside of the axon. Also, take a look at what else we have. On the outside here, we have a high concentration of sodium ions, a high concentration. So notice I wrote the sodium ions, the sodium ion large, and there's smaller amounts of sodium ions here on the inside. So the size at which I wrote these is important. The concentration is going to be in moles per liter. So we're going to put a bracket around here. The brackets mean moles per liter. So on the outside, we're going to have high sodium ion concentration. That's important. On the inside, we're going to have high amounts of potassium ions. Okay? Notice on the outside, there is some potassium ions, but they're in smaller amounts. Well, if you consider the ions here, and the ions here, and you factor in these negatively charged impermeable anions, which are stuck on the inside, what we have is a charge difference. So we have a difference in charge here compared to here. That charge difference is called a potential difference. And I want you to think of potential difference, think of it like potential energy. When there's a charge difference, you have potential energy. Just like if you have food as potential energy, gasoline is potential energy. If you take a rubber band and you stretch it and hold it, that rubber band has potential energy. And all potential energy can be converted into kinetic energy. So we can let go of that rubber band and we'll get a decent amount of energy of motion. We can blow up that gasoline and we'll convert the potential energy of that gasoline into kinetic energy, the kinetic energy of heat, light, and sound. So think of the charge difference as potential energy. This should make a little bit more sense once we kind of go through the discussion. So what's going on here? Well, let me grab an eraser. Here we are. high amounts of sodium on the outside, high amounts of potassium ions on the inside, plus we have these negatively charged anions. Well, if you kind of sum up the charges, so if you account for the charges here, and if you account for the charges here, remembering that these anions here are stuck on the inside, what we're going to have here is more negatives on the inside relative to the outside. So again, we're going to have more negatives here compared to there. And if you actually measured that potential difference, if you took a voltmeter and you put a voltmeter here and a voltmeter here, that voltmeter, it's going to be a microvoltmeter. If that voltmeter were placed here and here, we would register a charge that would be approximately negative 70.0 millivolts. So negative 70.0 millivolts on the inside relative to the outside. This negative 70 millivolts has a special name. It's called the resting potential. So that resting potential would be an unstimulated nerve that's just hanging out, resting. Again, understand that we have potential energy here because it's negative 70 millivolts inside compared to the outside. So that's important. Well, let's remember we have high sodium here, we have high potassium on the inside, plus we have these other, I'm going to rewrite it, these negatively charged anions scattered throughout here. What exactly is going to be happening in an action potential? So what I want to do here, so again, what we have here is a negative 70 millivolt resting potential. This negative 70 is compared to the outside. So what I want to do here is let's go through the general kind of steps in an action potential. Just listen now. You don't need to take any notes. I'll summarize exactly what you need to take here in a moment. So the key here, at least one of the keys, is understanding we're starting off with high sodium out, high potassium in. Let's get rid of this, and I'm going to write negative 70.0 millivolts on the inside there, but let's clean this up a little bit. And let's consider a resting nerve cell, and the resting nerve cell is a tiny bit negative on the inside compared to the outside. Again, that's a potential difference, and that's potential energy. That potential energy we're going to convert into the energy of an action potential, and eventually we're going to have a response all the way down at the end of the axon where those synapses are. And remember, you got to get to those synapses, and then just like domino effect, one synapse stimulates another nerve rides that action potential down the axon to another synapse. At that synapse, you're going to get neurotransmitters released, and boom, 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 boom. We're going to move that impulse along with that chemical communication in each synapse quickly from the periphery to the central nervous system up to the brain, and then elicit a response, sometimes really, really fast. Really, really fast. So here we are. We've got high sodium on the outside. We've got high potassium on the inside. So, and let's stimulate this axon. Stimulate it with a little probe, let's say. So we're going to stimulate this. So here's going to be one stimuli. And what's going to happen here, you've got these high number of sodiums on the outside, and these high number of sodiums all have a positive charge. So here they are. On the inside, we have a high number of potassium, but I'm going to put these potassium off over here, K positive, and We're going to look at those in a minute. But remember, we have these negatively charged anions here. And again, we've got that negative 70 resting potential here. So let's just worry about the negatives here. So notice I can put more anions here to represent that negative 70 millivolts. Now you can kind of see what we mean by potential energy. These negatives are really attracted to these, or let me say that again, these positively charged sodiums are really attracted to the overall negative charge on the inside of that axon. Again, think of that rubber band that's been stretched now and it's ready to snap. Well, this stimulus, what exactly does the stimulus do? The stimulus is going to create a local or regional permeability increase in this region of the axon. What is that stimuli going to do in terms of actually on the surface here of that axon? Well, if you recall, we know that this is a cell membrane, and cell membranes have proteins, and these proteins can do any number of different important things. Some of them are enzymes, some are cellular adhesion molecules, some are voltage gates. They are voltage gates which can open and close depending upon stimuli. So this voltage gate, which is essentially a protein, is going to be closed at certain points in time, but it can open at certain points in time based on the amount of the stimuli present. So let's stimulate this this axon here, and what's going to happen is these voltage gates will open up, and notice because of electrostatic attraction, notice positives want to come to the negatives. These sodium ions are going to begin to move into the inside of the axon. Now actually, it's electrostatic attraction. Certainly that's going to be important, but there's another reason that the sodiums are rushing into the inside. It's because of a diffusion gradient. We know that in typical diffusion, materials like perfume, whatever, oxygen gas in the lungs is going to diffuse into the capillaries. The oxygen gas is going to diffuse from the bloodstream into the tissues. Carbon dioxide diffuses. They're simply following the concentration gradient, which means, of course, moving from regions of high concentration to regions of low. So really there's two big things going on here. These are going to start moving in, and when they move in, they're moving in because of electrostatic attraction, but they're also moving in because of the diffusion gradient. High sodium here, lower sodium here. All right, well, let's say that this is a slight stimuli. You're going to get a little bit of these sodiums coming in, but it may not result in an action potential. Let's take a look here. Let's say that we're at resting potential. I'm going to draw kind of a rough graph here. Here's my graph. I've got time in milliseconds. I want you to copy this, and I want you to listen here, and then I'll kind of summarize it where you can take notes, but definitely copy this right now. So here we are. Resting potential is negative 70. So let's go negative 70.0 millivolts there. Notice the time's going to be in milliseconds. So this is going to be steady until the sodium ions begin to trickle in because of that weak stimuli. So let's just say this is weak. Well, how is this value going to change if sodiums are added to this value? Well, if you're starting off at negative and you add positives, we know that the negative 70 is going to rise. It's going to get a little bit closer to zero because you're adding positives. So with that first stimuli, you might end up with something like this. And notice now the inside of the membrane, and we'll put 0 here, and we're going to put positive 30.0 millivolts up here. So notice at this point, the sodiums have come in. They've trickled in, and we've increased that negative 70. We've moved the negative 70, increased towards that 0 number, and then positive 30 is going to be important, as you'll see in a little bit. Well, this was a weak stimuli. We didn't get an action potential. It was simply too weak to get that nerve fiber to fire, to shoot off that action potential. So let's add another stimuli. And let's make this stimuli a little bit stronger. So here we go. Well, with that stronger stimuli, we are going to open up these voltage gates for sodium, and now we're going to get more sodium coming in. As more sodium come in, take a look here. This number gets closer to 0. Let's say that we get to this region right here. Let's say that we rise from negative 70. Let's say that this is, let's go with negative 68, let's say. And then let's say we come to this region here. At this region here, that is the threshold potential. Threshold potential is when the nerve will actually fire. So we've added more of this sodium, and we've gone up. Now here's threshold. So let's make a note of that. And that's threshold potential. And at threshold potential, we're going to get a rapid influx of sodium. So we've hit threshold now. These sodiums are going to come rushing in, rushing in, rushing in. More positives rushing in, more positives rushing in, more positives rushing in. Well, how is, if we're graphing this, what would it look like when all these sodiums came rushing in? What you're going to see here is a spike, and it's going to rise up to about positive 30. And this indicates the sodium ions rushing in. At this point, we no longer have negative 70. So negative 70 has been reversed. And now at this point, we're at positive 30.0 millivolts. So here we are, positive 30. Again, I'll have some animations. I'll have pictures of graphical analysis of what's going on here as well. Now it's just important to listen to kind of get the idea here. So here we are. We're at positive 30. Right now, we have a situation where the original resting potential has been reversed here. So we're at positive 30 now. At this point here, we say that when you're at negative 70, we say that the nerve cell is polarized, and negative 70 is normal resting, so it's a polarized nerve cell. Polarized means one inside's negative, outside's positive. When we shoot up here, just some important terminology here, we've gone from polarized to depolarized. So at positive 30, right now, this is depolarized. All right? Well, this is an ion party going on. As all of these positives rush in, and as we reach positive 30, what's going to happen is that triggers a change in these proteins in the voltage gates. Except now what's going to happen at positive 30, those voltage gates which are in the cell membrane, the voltage gates for potassium now are going to open up at positive 30. What will potassium do if the voltage gates are opened up? What do you think they're going to do? They're just going to sit and hang out and associate with themselves? They don't like each other at all. They're positively charged. In fact, they're not happy one bit here for other reasons. Who knows? Who knows why potassium's not happy? But one big reason right now is because their repulsive properties, electrostatic repulsion, similar charges want to repel each other. These guys would get away from each other, and they will, but they'll only get away from each other when these voltage gates open. So, at positive 30 now, the voltage gates open for potassium. Right here, here, here. It's now open. Here's another one. And you're going to get the potassium rushing out. So, out we go, out we go, out we go, out we go. I hope you realize now this number is changing. We are now losing positives now. Why is the sodium or potassium, so ready to get the heck out of Dodge there? We've already said electrostatic repulsion, but there's also a diffusion gradient. Remember, we've got high potassium on the inside here, so it's going down its diffusion gradient as well as being electrostatic repulsion. So this is all happening in very, very short periods of times in terms of milliseconds. Well, if we're losing positives, that number's changing. We're losing positives. So this is going to start to go back down here as we're losing positives. So notice, more positives are going out. More positives are going out. More positives are going out. I've said that too many times. Notice, as the positives leave, we're getting more and more. We're removing positives. We're at 0. We still are removing positives. And we're going to go down, and actually we're going to overshoot this a little bit. So we're going to go a little bit lower than negative 70 millivolts. Well, so here it is. We had sodium rush in at the start, so the reds rushed in. And we hit threshold potential. This threshold potential can have differing values depending on where we are in the central nervous system. So we rushed in. There we go. Now, once we hit positive 30, we get the potassium gates opening. That's what happened here. And these potassiums are leaving. This is going down, so I'm going to put potassium out. Again, notice as the potassium leave, this number goes towards 0 because you're losing positives, and then you keep losing positives, so you're going below 0. We overshoot that value here. This overshooting of the value is called hyperpolarization. And I do want you to get this, okay? So hyperpolarization. Now notice, we're a little bit, we've overshot our resting, so we're a little bit lower. What's going to happen now? Let's take a look here. Let's go back to our action potential, or I'm sorry, let's go back to our axon. And here's where we are now, right here at this exact moment in time. We're at about negative, let's say negative 73 now. So we've overshot our resting potential. At this point, something's kludgy. Always wanted to use that word. Something's messed up at this point. What is it? What's messed up here? And what I'm talking about is what's messed up compared to where we started at resting. So if you look at your notes, I said to originally write write the notes of my original concentrations here, you should see that something's happened here. We've reversed, here it is, we'll give it away here. We've reversed the original concentrations of the sodium. Originally high sodium on the outside. Originally high potassium on the inside. Now though, at this point, at this exact point, we have high sodium in and high potassium out. So these are reversed, and at that point, you can't have an action potential, okay? So what do we do to reestablish the original concentrations? We got to get back to where we started with high sodium out, high potassium in, and there's a few of those anions that I talked about earlier that are stuck on the inside. Well, how do we do that? Notice it's happening right here. Notice we are getting a change going on right here. Well, have no fear, people. Have no fear. The sodium potassium pump is here. Oh yeah, the sodium potassium pump. This is an active transport pump. About 40% of all your cellular energy, if I'm not mistaken. Good enough number anyway, just to get the point across. About 40% of all your cellular energy is devoted to the sodium potassium pump. This is an active transport pump. Active transport pumps against concentration gradient. It requires a carrier protein. It uses ATP. This is an essential active transport process. And we mentioned this before when we talked about transport across cell membranes. Just to recap here, it never hurts to review, never ever hurts to review here. We talked about diffusion, mentioned that earlier, movement from high to low. We could talk about facilitated diffusion, which is movement from high to low also. And for example, glucose moves into cells by facilitated diffusion, movement from high to low, oh yes. That requires a carrier protein, but no cellular energy is required. We also talked about osmosis, diffusion of water into or out of a membrane, into a cell or out of a cell. In osmosis, we've got movement of water through a membrane. Doesn't require ATP. However, active processes like endocytosis, exocytosis, and active transport requires ATP. And the sodium potassium pump, I'm going to write it here. Have no fear, the sodium potassium pump is here. And the sodium potassium pump is going to reestablish the original concentrations, And now, at this point, let's use here. At this point here, we now can have another stimuli that again reaches threshold. We're not at threshold now, this is resting potential, but at this point we can stimulate the nerve again.